All right, welcome back, everybody. Okay, so I have posted homework 5, and I've decided to give a little bit of an extension on this homework because I want to include stuff that I'm going to talk about all throughout next week, Monday, Wednesday, and Friday lectures. So it's going to be due on Monday, November 24th. Before it was due on Friday the 21st, so this is just like the extra weekend and Monday. This is the Monday before Thanksgiving. And there won't be any class because I'll be out of town that day. Okay? So this homework, I think the first parts are pretty straightforward. So you're kind of showing some of these vector identities like A cross B is orthogonal to A and B. And you're showing that the divergence of a curl of a vector field is 0. Okay, those should be pretty straightforward by hand. Then we're doing some volume integration of some function. We're going to find the area or the volume under this function, and we're going to find the flux of a vector field out of that region. So we're going to use divergence theorem, which we'll probably cover on the Monday lecture. Okay. The fourth problem is a little bit, I wouldn't say it's difficult, but it's really important. So I told you that we wouldn't talk about infinite dimensional function spaces until after Christmas, and I apologize, but I lied. It's so important. So I'm going to bring this up again in ME565. We're going to start from scratch and really derive Fourier transforms for partial differential equations. But I want to get this idea kind of working in the background of your brain earlier. Okay? So what we're going to think about are inner product spaces, which are vector spaces that have an inner product. Okay, so probably next Wednesday or Friday, I'll tell you more about inner products and vector spaces and what that means. But in this homework problem 4, we're going to show that the space of bounded functions that are defined on the interval from x equals 0 to x equals 1 define an inner product space where the inner product is the integral of f times g. If this seems a little strange that we're defining functions as living in a vector space, it is strange. It's a very strange but important concept where functions live in a vector space called Hilbert space. It's a vector space with infinitely many dimensions. So unlike x, y, and z, you can kind of add dimensions to this vector space of functions forever. And we're going to show that if you take cosine functions, so cosine of pi times some integer x, then that defines kind of a basis direction in this function space. This is not actually a super hard homework problem. All of the steps are pretty straightforward, but I want you to start thinking about kind of what it means for a function to be an element of a vector space. And what does it mean for a basis element in that vector space? So this will all become a little bit more clear next week. Okay? Any questions about the homework or the extensions or anything? Okay. Okay, this is going to be really, really important when we start solving partial differential equations. We're going to be thinking about these functions, and we're going to be thinking about differential operators on this vector space of functions. Okay? And so that's what I'm going to talk to you about today. Are differential operators on vector spaces, which is just a fancy way of saying we're going to talk about vector calculus. Okay? So usually vector calculus is one of the favorite subjects of students, especially in engineering, because they're so useful and applicable, and you can describe so many phenomena with vector calculus and in kind of a coordinate system of dimension 2 or 3. Okay, so today we're going to be talking about div, grad, and curl. Okay, so the divergence, the gradient, and the curl of a function or a vector field. And we're going to do it using this symbol del or nabla. So the div is del dot, grad is del of, and curl is del cross f. Okay, so I think everybody has used this symbol del before, right? Yep. Okay. And what I really want to do today is a couple of things. So these are extremely important linear operators. I say that they're linear operators because they act like matrices and vectors. They have the same properties of linearity. But what we're going to find is that by writing differential operators as a vector of partial derivatives allows us to generalize the concepts that we're familiar with of calculus to arbitrarily high-dimensional systems, like we did for ODEs. And it's also going to allow us to eventually solve essentially calculus problems on manifolds. Okay, when I say a manifold, I mean a geometry that's not flat. So if you want to study how hurricanes move on the surface of the Earth, you're fundamentally not going to be working in a Cartesian coordinate system. You're going to be working on the surface of the sphere. And so you care about what the normal vectors are, and you care about working in a coordinate system that's actually relevant to that spherical geometry. In the example of the double pendulum, I care about these kind of circular coordinates. X, Y don't help me very much. But if I write my equations in terms of theta 1 and theta 2, my equations become much, much simpler. Okay? And so what we're doing here is essentially abstracting calculus to vector spaces. And eventually that's going to allow us to abstract calculus to kind of more general curved surfaces. Okay? Very, very powerful, super applicable. This really opens up most of the problems in classical mechanics that we would ever want to solve. Okay? Okay, so we're going to mainly be working with this del operator today. So sometimes it's called nabla. How many of you have heard of nabla? Right, nabla is not quite as common. So nabla, the funky Homo sapien, does not have quite the same ring to it. Okay, so del, nabla, and vectors of partial derivatives. How many of you listen to the music of Deltron? Del the Funky Homo Sapien? No? Gorillas? Yeah? Okay. So I have a hunch that that's where he got his name. Okay, so we're going to define this del operator as a vector of partial derivatives. So in the I direction, we're going to take the derivative with respect to x. In the j direction, we're going to take the derivative with respect to y. And in the k direction, we're going to take the derivative with respect to z, or z. Okay? And we can, of course, write this as a vector. So anytime we see this I, j, k coordinate directions, we can write this as a vector where this is in the x position, this is in the y position, and this is in the z position. So we have partial partial x, partial partial y, and partial partial z. Okay? Now, this is pretty cool because we've written this operator. So I'm calling it an operator because it operates on functions or vector fields. And it operates in a linear way, which is nice. So this operator del can be written as a vector. And so I can do anything with this operator that I can do with a vector. I can take the dot product. I can multiply it by numbers. I can multiply it by matrices. I can take the cross product and all of those things. Okay? So when I say that this is a linear operator, that means something really special and something really specific. So del is a linear operator because if I have, for example, grad of f plus g, so I have some function f and some function g, and I'm going to take the gradient of it, then that's equal to the gradient of f plus the gradient of g for all possible f and g. And I also have that gradient of some number times f is just that number times the gradient of f. Okay, so here f and g are functions of, so f is a function of x, y, and z. G is a function of x, y, and z, and alpha is a number. Okay? So the fact that these two properties are true for all functions f and g, and for all numbers alpha means that this del or gradient operator is a linear operator. Okay? So what are some other examples of linear operators that we've seen before? Okay, the derivative is definitely a linear operator. Because if I take the derivative, I mean, this is essentially a vector of derivatives. So we're building this on the fact that the derivative is also a linear operator. True? So the really, really important one is matrix multiplication. Okay, matrix multiplication, or multiplication by a matrix A, can be thought of as a linear operator. Okay, so if I have a matrix A, then A operates on things. It multiplies vectors and gives you new vectors. Okay, so A is an operator, and A happens to be a linear operator because A times vector 1 plus vector 2 is the same thing as A times vector 1 plus A times vector 2. Okay, so matrix multiplication is kind of the classic or most intuitive example of a linear operator. Okay, and so the idea is anything we can do with matrices, everything you've learned from linear algebra, like getting orthogonal directions and basis sets and Gram-Schmidt and solving equations, you can do with other more general linear operators. And this gives us a nice way of thinking about these calculus problems in terms of linear operator theory. Okay? And this is going to be really, really important when we solve partial differential equations, because when our partial differential equation is only written in terms of these linear operators, it's going to be way, way easier to solve. Like, those are the partial and ordinary differential equations we can solve, are systems like x dot equals a times x. We can solve this because a times x is a linear operator, and so my solutions superpose. My e to the lambda 1t and my e to the lambda 2t and all of my e to the lambda t's, I can just add up those solutions, and there's still a solution of my system. That's because of the linearity of matrix multiplication. Okay, so linearity is a super, super important property of this gradient operator and of derivatives. And this is something we're going to revisit a little bit later. Okay, so this is my del operator. Del is just a vector of partial derivatives. And the first thing we're going to do to this, this operator is we're going to multiply it by a scalar function. Okay, a scalar field, essentially. So if we have the gradient, then the gradient is defined as applying this linear operator to a scalar function f. Okay, so this linear operator applied to some f of x, y, and z is called the gradient. Does anyone know why this is called the gradient? Why this is a good name? Sorry? Yeah, exactly. If I thought of f as a contour map, like maybe this is the topography of Washington State, and the coordinates were just x and y, then this gradient would be how steep that, that contour surface was, how steep the mountains are in the x and the y directions. Okay, so it kind of measures how fast my function is changing in these different directions. That's the gradient. Okay, and so we say that grad f is just partial f partial x, partial f partial y, and partial f partial z. So this is kind of cool. We took a scalar function. This is just a number for every point x, y, and z. And we've now defined this vector of the gradient of s. And this vector could define a vector field. We could integrate an ODE using this right-hand side, this vector field, which we did before. Right? When in gravitation, we said force equals minus grad potential. And then we said, well, force equals mass times x double dot. Okay, so that's the same gradient that we're talking about here. We can take a scalar function like my mountain height, and then using the gradient, I can tell how fast a ball will roll down that height by integrating this ODE. Okay, super useful. Before, we talked about really, really simple toy examples like a bead on a 1D hoop or a 1D wire. But now we can start thinking about things like, this thing could actually be a two-dimensional surface, right? And we can write the gradient of that two-dimensional surface, and then we can get a multi-dimensional gradient field, and we can integrate that ODE. Okay? Questions before we do an example? Okay. So this is probably mostly review, but I really want us to get the fundamentals. And I also want us to say this in the language that we're going to be using later. So we might not have all heard about this in the language of vector spaces. And so I think that's important to kind of go through these examples starting from scratch. So one example is a mass in a gravitational field. Okay, and a gravitational field is just a very, very special type of potential field. Okay, so where do we start with gravitational potential problem? What is kind of the ground floor, what's the ground truth of gravitation that we start with? Okay, so masses will accelerate in a gravitational field, but how? What makes them accelerate? Forces. Okay, what kinds of forces do we have in a gravitational problem? Okay, attraction. So we always start with Newton's universal law of gravitation as long as our masses are not extremely large or extremely small, right? So for everything within 10 orders, maybe not 10, 7 orders of magnitude in either direction of our masses, we can use Newton's law of gravity. Okay, so we have Newton's law. And that law says that the force that I feel, force is a vector, right, because it points in a direction. So this force is equal to minus little m times big M times g divided by radius cubed in the radial direction. So I'm writing it in terms of a vector. So little m is the mass of my object. Big M, let's say that this is the mass of Earth. And g is the universal, or at least approximately universal, gravitational constant. Does anyone know if this is still a constant? So constants in physics are always subject to change with new data. Has anyone ever shown that this is different anywhere? Okay, let's say it's still a constant. You could equally well think about this as the gravitational field of an asteroid with a spacecraft landing on it. Okay? In fact, this is exactly the kind of vector calculus that was just done to land a spacecraft on an asteroid. You have to compute this nasty force field because this thing is not a sphere. But we're going to assume that Earth is a sphere, and this problem becomes a lot simpler. So this is a little different than what we're used to because we have a divided by r cubed. But we know that the gravitational attraction force is proportional to inverse of r squared. So where is that extra r coming from? Why do I have an r cubed here? Right, so my r vector also has a magnitude of r. Okay, so if I'm in the direction r, I need to normalize r and then the magnitude of my force is proportional to 1 over r squared. Okay? And we've kind of already looked at this before, that this is equal to minus the gradient of some potential field. Potential energy field, okay? And we're going to say the gravitational potential it's my favorite abbreviation is POT. I just love that abbreviation. Okay, so we have this gravitational potential, V equals minus mg over r. And this is just a scalar field. For any radius you're at, doesn't matter what direction you're pointing, this is what your gravitational potential is. Okay? Just a scalar field. So this is a scalar. Now, this doesn't look like the gravitational potential we used for the particle in a bead, the bead in a wire. Right? What is different between this potential energy and the potential energy that we kind of have done for this bead on a wire? I had like a minor crisis this morning when I was writing down these notes because I wrote this down and then I wrote down the bead on a wire and they were different potentials. Why are these different potential energies? They're both in Earth's gravitational field. Well, so as long as our radius, so essentially whenever we do a problem like the bead on a wire, we are linearizing about the Earth's radius. Okay, we're kind of linearizing this gravitational potential about Earth radius, which as far as this experiment's concerned, I'm experiencing the exact same gravitational attraction if I'm 1 meter higher or 1 meter lower. It's negligible, the change in Earth's attraction due to my 1 meter increase or decrease of radius. And so I linearized this gravitational potential about radius plus, essentially you can linearize about Earth radius. Call that r0. And so if you take this function 1 over r and linearize it about let's say we're at 1 over r plus h, and linearize this about r naught, you'll get the typical gravitational potential that we're all used to seeing, which is mgh. Okay? Just something to keep in mind, that when we talk about, kind of Earth-sized distances, we have to use this gravitational potential. When we talk about lab experiments, we're talking about a linearized potential. Okay. Okay, so we have this Earth. Can't really draw Earth. There's part of it. And we know that all of the directions point in to Earth. So this is essentially the force field that we're experiencing. And we also know that the magnitude is smaller the farther out you are. Okay? So that's one of the things we know about this potential. So what we can do is we can take minus gradient of v and essentially compute the x, y, and z components of this gravitational velocity field. And I'm going to write my radius like this. I'm going to say it's minus m times big mg over the square root of x squared plus y squared plus z squared. So I'm making life way more difficult for myself by choosing Cartesian coordinates for something that should definitely be written in spherical coordinates. But we'll talk about spherical gradients later in another lecture. Okay, so we're just kind of getting a feel for how to do this. So first we take partial v partial x. And that equals something nasty like minus little m big M g times 2x divided by 1/2 x squared plus y squared plus z squared to the 3/2 power. And these 1/2s cancel and my negatives cancel, and I get something like this. Okay, if you take the partial derivative of v with respect to x, you get this. Fortunately, this denominator is actually simple. This is just radius cubed. Okay, so it looks nasty, but it's not that bad. We just get a radius cubed in the denominator. Partial v partial y is the same thing, big M g y over radius cubed. Partial v partial z is little m big M g z over radius cubed. Okay? And so our force vector, which is minus grad v, is equal to this in the I direction plus this in the j direction plus this in the k direction. Okay, that's what my gradient means. And so this equals this vector field. Okay? So now, for every point in space, for every x, y, and z location you can name in the universe, or in the near-Earth universe at least, this is the gravitational force vector, and it points into the center of Earth. At all points, it points to the center of Earth. Okay, so this is essentially one way of deriving the force vector field from the gravitational potential using the gradients. And it's pretty straightforward. You just take partial derivatives and stack them in a vector. Okay, and if you plot this in something like MATLAB, you'll find that you get exactly what you expect. You get all arrows pointing into the center of the Earth. They're stronger the closer you are. They're smaller the farther away you are. Okay? Okay, any questions about the gradient? You can use the gradient for optimization. Like, let's say I have some cost function j of x. Let's make it a little more complicated, x and y. So I have this bowl. Okay. So I have some cost function j as a function of x and y, and it's just this parabolic dish or bowl. Okay. If I want to find the minimum cost values for x and y, what I'm trying to find are values of x and y that make my partial derivatives equal to 0. Okay, so I want partial j partial x to equal 0, and I want partial j partial y to equal 0. This will be true at my optimum minimum point of this cost function. Okay, so optimization is one of the most important fields of all of applied mathematics. I almost can guarantee that at some point in your careers, you'll all do optimization at some point of something. And the simplest and most kind of intuitive type of optimization is called the gradient optimization. And this is based on Newton's method of finding zeros of a function. So essentially, we're trying to find zeros of the gradient of j. So we want grad j to equal 0. Okay, and the way we do that is we start at some point, and we look at what the gradient is and where it's pointing, and we take a step in that direction. And then I look at where the gradient is now, and it's now pointing this way, so I take a step in that direction. And now I look at where my gradient's pointing, and I take a step, and I keep kind of walking towards this optimum point. And so using Newton's method on the gradient of j, you can walk towards an optimal solution. This is called a gradient descent search, and it's the most popular mathematical optimization technique. But again, it's built on the gradients. And it totally generalizes if I had 15 variables. I could still do a gradient search. I just need to compute this 15-dimensional vector of partial derivatives with respect to each of my coordinate directions. Okay? We will talk about optimization a little bit more. This is a really, really important idea in data science. And so we'll probably talk about this more in 565. Okay, good. So now I want to tell you about the divergence. So that was the gradient. Gradient's really important. Today I'm going to try to get through div, grad, and curl. And then in the next lecture, we're going to talk about the conservation laws and kind of integral calculus theorems like the divergence theorem and the Stokes theorem and Green's theorem, okay, because these are super important. Okay, so now we're going to talk about divergence. So what's the physical intuition about a divergence? What does a divergence mean physically for a vector field? Maybe I should write it down first. I'll think about this while I write it down. Okay, so with the gradient, we saw that we could take a scalar function. It's just f of x, y, and z. And when we took the gradient, it became a vector field. Okay, so for every point x, y, and z, I now get a vector, and it points in the direction of the gradient of f. So since del is a vector, I can take the inner product also. But what do I need to take the inner product with? Another vector, right? I need another vector. So essentially, with a vector f. Okay, so let's say that I have my vector f of x, y, and z, and it equals f1 of x, y, and z, f2 of x, y, and z, and f3 of x, y, and z. Okay, so now I have a more complicated function. It's still a function of space, x, y, and z, but now at each point in space I have a vector. So this is a vector field. And in fact, it could have been a vector field obtained by taking the gradient of some scalar function. Right? No reason not to. So the divergence is del dot f. The dot product of my gradient operator, or of my del operator with this vector field, is the divergence. Okay, and this is just a number. Anytime I take the dot product of two vectors, I get a number out. So before I took the gradient of a number and I got a vector, now I'm taking the divergence of a vector and I'm getting a number. Okay, so what this looks like, if I take the dot product of my vector of partials with this f, I just get del dot f equals partial f1 partial x plus partial f2 partial y plus partial f3 partial z, just a number. Okay. Now, what does this intuitively or physically mean, this divergence? How many of you study fluids? A little bit. Okay, only a couple. So the divergence measures whether or not my vector field is expanding or contracting or keeping volumes the same. Okay, so the divergence literally measures how much particles in this vector field will diverge. Okay, or converge, or not move at all with respect to each other. Okay. So we're just going to do this on 3 examples, and this will really clearly paint the picture of physically what this is doing. Okay, so example 1 is this vector f equals x in the I direction plus y in the j direction. So we're dealing with a 2-dimensional system, so my del is partial partial x, partial partial y. Okay, and so div dot f is just partial of this term with respect to x plus partial of this term with respect to y, which is just 1 plus 1. Okay? So this equals 2. Does that make sense? Yeah? Okay. So this is a positive divergence. And if I plot this vector field, what it looks like is Okay, so let's pick x equals 1, y equals 0. Then my f is pointing in the positive 1 direction. Let's pick x equals 2 and y equals 0. Then my vector is pointing in the positive 2 direction. So it's increasing in magnitude as I go away. Same thing with y and both of these. So in all directions, this thing is kind of expanding outward and accelerating as it goes. Okay? A positive divergence means essentially that my flow field is diverging. That's why it's called divergence. This is written by people who spoke a language, and they picked a word that meant the same thing as what this actually does. Okay, so that's what the divergence does. Let's try another example. So example 2. Let's make a field that points inward. Same field, except I'm going to put negative signs. F equals minus x in the I direction, minus y in the j direction. So what's this divergence? Minus 2. Del dot f equals minus 2. And what does this vector field look like? All of my arrows are pointing in, and they point in faster the farther away I am. All right, so same deal. Okay, so if I have the positive divergence, then this is essentially saying that the flow is diverging. Here we can say that the flow is converging. So negative divergence, the opposite of divergence is convergence. Okay, and then we're going to look at a final example, example 3, which is my vector function f equals minus y in the I direction plus x in the j direction. Okay, should we compute the divergence first, or should we plot it first? Plot. Which one? I heard compute the divergence first. Let's compute the divergence first. Okay, so how do I compute this divergence of f? What's the first thing I do? Okay, I take partial x of the I component. So partial y, partial x is 0, plus partial of the j component with respect to y, which is also 0. So this divergence is 0. What that picture looks like is the following. So let's say that I am at a point x equals 1, y equals 0. So I'm at this point. Where does my vector point? No, like where does my function f point at x equals 1, y equals 0? So in the positive j direction, right? Because I have 1 in the j direction. So I've got a 1 here. Similarly, if I was at x equals negative 1, I would have a down in the j direction. Right? That's how we read off this vector function. If I had y equals 1 and x equals 0, I would be pointing in the negative direction like this. And similarly, in the positive direction for y equals minus 1. Okay? And so I get this kind of rotational flow. So this is a pure rotation. In fact, this is what we got when we solved that differential equation. If I solved x and y dot equals 0 omega minus omega 0 of x and y, I would get this vector field. It's the same vector field, basically, as this differential equation. Okay, so what it means when divergence is 0 is that this flow is neither expanding nor contracting. We say that it's incompressible. You can't make its volume smaller. You also can't make volumes larger. So we say flow is incompressible. At least that's what we say in fluids. There's probably other terms in elastics. I think you would call this the continuity equation. So I want to just draw this as a picture because I think this makes a little more sense. So imagine that I started with some initial blob in each of these locations of a certain volume. Okay, what happens to this blue blob in this diverging flow? Right, all of those, let's say I literally just, this is a fluid flow, like when you turn your sink on in your faucet, when you turn your faucet on in your sink, water comes down and it creates this expanding flow outward. And if you put a little bit of blue dye in the sink, what is it going to do? It's going to go outward and it's going to expand in volume. Okay, so it's going to end up here. Now, what about this example? This is like if I have my bathtub full of water and I pull the plug. Now all the water is coming in towards the center, so this is a sink. And if I have this initial blue dye, it's going to get converged into a smaller volume. Okay? And this blue dye is essentially just going to be rotated, but it's going to stay in the same shape and it's also going to stay in the same size. Okay? This is like if I had some object in a vortex, in a tornado or a hurricane. Okay? These are, essentially, you can think of these as the same vector fields that are being defined from our ordinary differential equations before. Okay, so it's really, there's a pretty strong connection from vector calculus to ordinary differential equations. Okay, any questions about the divergence? Okay. So finally, we're going to talk about the curl. So why are there just 3 of these operators, div, grad, and curl, that we normally talk about? Because this del operator is in essentially a vector space. It's a linear operator on vector valued functions. And we have dot products and cross products. And those are kind of the essential ingredients for these inner product spaces. So if you had extra structure for an extra special vector space that you invented, you could define a new operation with del. That would be fine. So the curl of my vector field f is given by the cross product of del with f. And remember, from the last lecture, we can take this vector del, and whenever we take the cross product of a vector, we can write that as a matrix. Okay, so we could write this as like, oh, there's no way I'm going to get this right. Let's say 0 minus partial partial z partial partial y minus partial partial y partial partial z 0 minus partial partial x partial partial x 0. Right? This is del cross. I might have messed up the negative signs. I think this is right. I don't remember. Okay, and so if we had that same f as before that had f1, f2, f3, then we can write the curl as curl cross f is the determinant of this matrix. F1, F2, F3, the 3 components of f. It's the same as multiplying this by f. Okay. Okay, before we talk about what this means, let's do a super simple example. Okay. So if f equals xy in the I direction minus sine of z in the j direction plus 1 in the k direction, then I would plug in, I'm just going to plug in these components. So f1 is x times y. f2 is minus sine of z. And f3 is just 1. It's just the constant 1. And so I can take this determinant of my del operator crossed with my S vector. And I get, okay, so in the I direction, what's partial y of 1? 0. Okay, partial z, so minus partial z of sine of z. So minus cos of z. So I get 1 cos z. Okay, in the j direction, so minus j times partial x of 1, partial z of x times y, also 0. No z's in here. So 0 in the j direction. And then in the k direction, I have partial x of sine z is 0, and partial y of xy, just x, and there's a minus x. So curl of f is cos z in the I direction minus x in the k direction. Okay, easy to take the curl of something. You literally just take f1, f2, f3, and you plug it into the definition of the cross product. Okay? So there are some physical interpretations of what the curl means. So one of the most obvious interpretations of curl is in fluids. If I have something rotating in the fluid, so the thing I just erased has a curl because it has a rotational component of the fluid. So curl measures rotation in my vector field, whether or not particles rotate or not. So it picks up vorticity. If I take the curl of my velocity field, then I get vorticity, which is a measure of how much things are spinning. Like tornadoes have a ton of vorticity. Hurricanes have a ton of vorticity. Another example is if I have some rotating solid object like an asteroid. Okay, so let's say I'm trying to land on an asteroid. And this thing is rotating about some vector w. And the length of w is its rotational rate, omega. And if I am looking at some point at some radius from the origin, then we know that w cross r is that point's velocity. Okay, so the velocity of any point in this asteroid that's rotating is given by curl of the rotation vector with the radius vector from the axis of rotation of that point. Okay? And if I take the curl of this vector field v, I'll find that curl v equals 2 omega. So the curl of v measures twice my rotational speed at all points. So this is in the notes. You can work through this kind of more carefully and actually show that this really is 2 omega. But what I'm getting at is that the curl measures rotation. The curl of a vector field measures rotation. In fluids, in solid bodies, in any system, if you have rotation in your vector field, the curl pulls out the rotation. Divergence pulls out expansion and contraction. Curls pull out rotation. Okay, that's the geometric interpretation. Okay, that's all I have time for today. In the next lecture, we're going to talk about the vector calculus theorems like divergence theorem, Gauss's theorem, Stokes' theorem, things like that. Okay?